We can transfer to our second speaker.
All right, thank you, Sujit, for the very interesting talk. And now I'm going to introduce our second speaker of the night, Sydney Hemenway. So Sydney grew up in Arlington Heights, Illinois, with her brother and dog. She flew across the country to go to UC Berkeley for her undergraduate joint degree in material science and electrical engineering and computer science. Her undergraduate research focused on electrochemistry and turning carbon dioxide into fuels. Now she is doing a PhD on sodium-ion batteries at UC Berkeley, and in her free time, Sydney enjoys trying unique produce at Berkeley Bowl and making her own postcards. No way.
Thank you for the kind introduction, Caitlin. Yeah, so you heard a little bit about me. My name is Sydney, and I study material science. And I'll go into a little bit about what that entails if you haven't heard of it before. So I'm here to discuss if sodium is the new lithium and how table salt might save the energy storage industry. So this is a photo of me showing you how I got interested in material science when I was younger. So I'm like 16 years old, my hair is different. And in this photo, I am trying to make a solar cell. In high school, I was really obsessed with this idea of renewable energy because the sun will shine on a good day and we can extract its light in the form of electricity and make energy basically for free. So why not take advantage of all these renewable energy sources? And I was like, oh, as a material scientist, I can design these materials that harvest and capture energy. So why not try it out? I'll major in that and learn more. So I still believe renewable energy is promising. This is a graph of renewable power being supplied to California throughout a typical February day. So what we see is that in the morning, renewable power can reach around 50% of our demands needed to power our households. And around noon, we have a super big peak in solar energy. This graph tells us a couple of things. One, that renewable energy is intermittent. So solar peaks during the daytime on a non-cloudy day, and wind peaks at night when the wind flows faster. Some sources like hydropower can be available throughout the day, but all in all, renewable energy is intermittent. One other thing to notice about this graph is renewable energy is not that limited, at least in California. We've invested a lot in renewable energy, and we can get renewables to supply 50% extra power than what the state actually needs. The biggest challenge here is actually using this 50% extra power and not throwing it away, so that we can power our homes at night when we want to watch TV or play on our laptop. So renewable energy is promising. It's economical. People are trying to install solar panels. It's the most affordable it ever has been, but it requires energy storage. And so that's what I'll discuss today. And to really hammer home the point of renewable energy is great, but we need something else. In 2017, the LA Times published this paper or this article that California invested so much in solar power that we had to sell it to Arizona. Like we were producing so much extra power that we couldn't even shed that electric load until we paid another state to take it from us. So it's really cool that we have this renewable energy, and yes, California is somewhat unique, but we do need energy storage sources to really harness this power. So I want to ask, yeah.
Like, what's the reason that people, like you said, they were paid to take the energy?
Yeah, I need to read more about this article in particular, but I think it's because once you have the grid, the grid needs to operate at certain conditions, like it has to operate at a certain voltage, or the current or the amount of electricity being passed through our wires must be maintained so that the wires don't burn out or something like that. And if we don't have enough light bulbs turning on or something to dissipate that power, then our grid will be unstable and we'll have blackouts. So I think that's like the extreme version, but you can read more about this article if you like. Any other questions so far? Okay. So now I'll ask you all, solve our energy crisis. Like, what are our energy storage options? Anything that you can think of that you use on a daily basis? Batteries, yes, the point of this talk. Anything else?
Anything I can think of.
All good, all good.
Do we sometimes like dam rivers differently depending on?
Yeah, perfect. Okay, so I expected answers like batteries and also answers like hydropower. So where we turn our water, we like funnel our water up to some area that's high in gravitational energy, store it there, and then when we need energy, we'll let the water flow and turn these turbines, get some electricity. Some other things that are energy storage options are just like chemicals, like wood, which we burn. Not that efficient, but it's still energy. It could even just be food, like we eat food, there's calories in it, so there's some sort of energy storage. So I would divide this into like 3 main paradigms of energy storage. One is like fuels. We take it, we burn it, it goes away. Another is some sort of renewable energy, which is like renewable energy that's also storable, so like nuclear energy or hydropower, because we can just store that water. And then I would also talk about batteries, and maybe this hydrogen energy should also be in that sort of fuel area. But the main cool thing about batteries is that batteries can be recharged. So it's not like fuel where it'll just go away and we need to purchase more every time. We can just plug it into a socket. And unlike nuclear or hydropower, which require super large investments and political fiascos, batteries are very modular and they can fit in the palm of your hand. So I am really interested in batteries because they can be used in many different technologies and they're super small, hopefully portable, things like that. So the main batteries you may have heard of are lithium ion, like the ones in your phones or your laptops, or even electric vehicles. But lithium ion batteries also have some costs associated with them. One thing about lithium ion batteries is that they often involve cobalt, and 70% of cobalt is mined in the Congo in near slavery-like conditions. So it's a pretty unethical supply chain to have lithium ion batteries. Another thing about lithium ion batteries is that 90% of lithium is produced in 3 countries, none of which are the United States. So we're very dependent on geopolitical factors to get our batteries and our energy storage. Another thing about lithium ion batteries is that the materials involved are inherently expensive or subject to price fluctuations due to the geopolitical risk. So the material I'm mentioning in the next slide is 100 times cheaper than this per ton of raw material that would go into our battery. And lithium ion batteries are amazing in that they store energy, but they also do involve some mining. So you can imagine just like cracking in at some stone site and crushing these particles and extracting the lithium that way. So more and more of our mines are coming from this intense ore mining. So on the other side, sodium ion batteries promise all of the other things. So sodium comes from sodium chloride, which is like table salt, or sodium carbonate, which is in like our lakes and our oceans. So it has an ethical supply chain. We have a lot of salt in this world. Sodium is also very abundant. It's the 6th most abundant element in the Earth's crust. And the US has so much that we can export 40% of it to other countries. So we're not really dependent on geopolitical factors to get our sodium. Another thing about sodium, which I already alluded to before, is that it's pretty cheap. It's 100 times less expensive in terms of the raw material than lithium. And it can be produced from, like I said, these salty waters or brines, not necessarily ores. So you may be thinking, if sodium is this much better in our abundance or the cost, why don't we have sodium ion batteries in our laptops? Well, the biggest challenge is sodium size. So this is a lithium and this is a sodium ion. Sodium is 1.3 times larger and 3 times heavier. And the way this manifests in our batteries is something like this. So in our battery, think of your like cylindrical battery. There are two different sides. One is shown on the left and one is shown on the right. And what happens is these ions must move back and forth different sides of the battery when you're charging and discharging. So one thing that would happen is if sodium is 3 times heavier, our whole battery could store much larger mass. And we don't want to carry around big bulky laptops. I mean, my back already hurts. And the other problem, like I said, is if sodium is 1.3 times larger, we also have a challenge of fitting sodium into our known chemical structures. If this is difficult to visualize, don't worry, I'll show a little animation here. So we can think of lithium and sodium as different species that must fit inside of our structure, inside of our material. So let's play basketball with them. So here I'm showing lithium, and because lithium is so small, you'll always score. You'll always be able to fit sodium inside of a hoop, and it'll pass through and be stored easily. Sodium, on the other hand, is large enough that it is pretty difficult to store the sodium. So if I were shooting hoops, I mean, I wouldn't even want to pick up a ball that was 3 times heavier. So it's difficult to fit sodium in. Normally it would hop out, or if you really manage to force it in, the rim itself would be distorted. And that's what happens to these crystal structures. They may expand as you force sodium inside. So as a material scientist, I'm here to offer solutions or promises, and material science can try to improve these chemistries. We typically start with like the processing, like what Sujit had mentioned for his materials. And then we look at the structure of our materials to eventually measure our properties and performance. So it looks something like this, where we have our salty brines and we do reactions with them to get some structure, where this is like some sodium ions inside of some host material with like layers of oxide, layers of sodium. And then we would measure something like the properties. And so what I'm measuring here is like the voltage, or the amount of work we would have to do to move an electron inside of our material, and how much our state of charge is. So when our battery starts at 100% charge, we can measure its voltage decaying in time as our battery is discharging. And this is a lot of what material scientists and battery scientists do. From this graph, we can learn things about the performance of our battery. So our energy is just the voltage times the charge, or just this area under the curve. And our power is very similar plot of just voltage times the current. So we need to understand our processing, our structure, and all of these things to understand how a battery works. The way that I am approaching this is by changing battery chemistries. So what we have is like a typical layered material here that people have used for lithium-ion batteries. But because, like we said, it's hard for sodium to actually fit inside of the structure without the layers expanding, I am looking at new chemistries where sodium can have a different environment around it. So this is a different chemistry where sodium is not in a layered structure, and it sees different environments from like oxygen and other metals. And what I'm doing specifically is seeing if these new structures can be fast charging. If they can have a higher power density than what their original materials were, then maybe they'd be even more useful as batteries. And also, if these materials have a different structure, they may have different voltage implications. So we may have higher energy just from changing the chemical structure. And one other cool thing about this is that if this structure is more thermally stable, like if we heat it up and it's less likely to blow up or less likely to decompose, we need less cooling modules. So the battery itself can be smaller, and it could work for electric vehicles and things like that. So these are the three main ways we can try to improve our battery chemistries to involve sodium. And so what I'm doing in my research is this pipeline where I start by using computers to do all of those processing to performance steps and checking 5,000 new battery materials. This helps me down select materials so I can recommend them to experimentalists and to robots to make these top candidates and check their properties. This pipeline is pretty cool because not only is it like more predictive and quick than like an 18-year technology development cycle, it's also a lot safer and less expensive. Like, I don't want to buy 5,000 raw materials and just plug and chug them together. Yeah, so this is what I'm doing with my work and my colleagues. I am not alone though. Many companies are developing sodium-ion batteries. If you're interested, you can follow along with Natron Energy, who's trying to scale up sodium production in the Midwest, in Michigan. And lots of other battery companies like BYD and CATL in China are also investigating sodium-ion batteries. So the future is now. People are really trying to get involved in sodium battery technology. So to recap, we've learned that alternative batteries like sodium can make promising batteries because of these reasons. Like, it's ethically sourced, it's abundant, it's cheap. And the biggest challenge with sodium is that it holds less energy than the lithium counterparts, like maybe 80% of what a lithium ion battery could do. So with these constraints in mind, we think that sodium ion batteries may be wonderful stationary energy storage. If they're so heavy, we don't have to move them around. Let's just put them on our grid and harvest our solar energy or retain it right there. So I hope this talk gave a little insight into sodium ion battery research and gave you a little bit of tips on how we can make a sustainable, ethical, and secure energy future. Let's use table salt to power the world. My acknowledgements, just my PhD colleagues and lots of people who helped with my presentation. Do you have any questions?
I can start off then. So when you're looking at kind of forming the structures around those sodium atoms, is it that the actual structure helps assist with like how much storage capacity you can have, or is just kind of more of it allows there to be more of the sodium atoms and therefore more higher energy density or something? Like, is the question more so we just need to pack more sodium atoms, or does the structure around it actually do something?
I think the main idea is like sodium must be stored there. So if you are not using your battery, you expect it not to lose charge. So the sodium must be stable in that structure. So that's why designing that structure is important. Now, if that structure can fit more sodium per volume and mass, that's great. It's only like one factor. Like, if that voltage is not high enough, your energy won't be high enough. So batteries are a lot of trade-offs. Like, keep this material stable, pack it as much as you can, don't let it decompose, all of that. Does that answer your question?
Mm-hmm.
A similar question to the other presentation. Are there any companies that are actually making sodium batteries now, or are they all kind of in like a research and development process?
Yeah, so Natron Energy, Natron is just the original, like, you may recognize sodium has Na. I think Natron just means sodium. So Natron is a startup that is making pilot scale battery plants just for sodium ion batteries. And I think a lot of these people are trying to mass manufacture them. Yeah.
It's silly. But I've never been told to eat a lithium battery. Could you in some way consume a sodium ion battery?
I need to think about that. I'm not a health expert, but probably not. I think a sodium ion battery is still similar to a lithium ion battery, that you still need some sort of metals inside. Also, one of the like liquids in the batteries is typically not like water based. So I wouldn't recommend it.
Are there other battery types that you're exploring?
Yeah, so, oh, I wish I had a picture of the periodic table. So lithium has lithium can form just elemental lithium with no charge or lithium plus, and sodium can also form sodium or sodium plus. If you keep going to heavier elements, there's like potassium and cesium, but the heavier the element is, the more difficult it is to move around and the heavier our battery would be. So we're picking sodium because it's the next level of like slightly more massive, but it's more abundant. Does that make sense?
I'm curious about the supplies of sodium. Let's say that it goes global and we use only sodium batteries. What happens to the supply of sodium? Where is all of it coming from? Is it being mined from the earth, evaporated from saltwater sources?
Yeah, so a couple of things. I think most of it would come from brines. So like ocean water, or if you have like the Salton Sea, which is super, super salty, then you could just evaporate water from that. I would say that's the main option. We still have to see it at scale, but since it's the sixth most abundant element and more geographically spacious, it may be okay to scale up. Yeah, but we still have to see how companies react to this, like where they source their lithium from.
You know, I was just thinking if we're evaporating it out of brine, now we have water without salt. Could we take care of two processes here and get sodium for the batteries and clean water, potable water for our needs?
I think that is a great idea. I need to look more into if sodium or sodium carbonate is the only thing in that water. So it would be super hard, at least from my perspective, to get all of the trace elements out of just that water stream as well. But that's a great idea.
You could get cruise ships too, you know, as they're getting their water over to store some of that extra salt.
Yeah, that'd be awesome.
I was just thinking about how, like, with batteries, you're not supposed to throw them in the trash, right? Like, we collect them, and like, it's not necessarily easy to like recycle batteries and everything. And I'm assuming for lithium, if like the materials we're using are already not abundant, it's probably more important to like recycle them. And like, is that a problem with sodium too? And have you read or thought about or heard about any research on like sodium ion battery recycling?
Yeah, so I think because sodium ion technology is not that pervasive yet, it's hard to incentivize a company to develop recycling facilities. I will say, like, one of the reasons that people are reluctant to switch even just to lithium, so like your car lights are powered by like lead acid batteries, which is a whole nother type, is because lithium is not recycled fully yet. So yeah, recycling is a big factor, but we hope that it'll come in as the technology progresses. Any other questions or thoughts?
Might be something very basic. I somewhere read that it's like they use porous materials as a, like instead of graphite as the other electrode, lithium as graphite. In sodium they use like porous carbons or something. Is something similar you also use, or?
Yeah, so
What was the question? I didn't quite hear it.
Like in lithium batteries, they use graphite as the counter electrode. So you have a lithium and you have graphite. But in sodium, you have to use porous carbon or something like that.
yeah, so I think you're referring to like this side of the battery.
Yeah.
So yeah, sodium is unique in that you don't you need to develop all aspects of the sodium ion battery. So I'm only working on one side just because that's where my expertise will lie. But you're right, like porous carbon will be useful for the other side. Sodium can't fit in here because, like I said, like sodium's too large. So there's like a lot of interlayer expansion, and this material is not good at storing sodium yet.
Question is like, because as a person that's sort of talking to my phone, I feel like when we use our phone for maybe a couple of years, the battery is kind of like situation or performance will be going down. So with that, this kind of battery performs better. So like I see you mentioned that it's only kind of 80% of the energy storage, but I don't really care about. I want to know if like after 9 years or 10 years, would that be still perform really good as before?
Yeah, so a couple things on that. So one is, yeah, like battery materials can degrade over time. If you give something enough time, maybe it'll decompose spontaneously or it's too hot, something like that, and this material itself will break apart. So there's that materials challenge. I think one other aspect is like your phones know how to read these plots that I have to generate for my research. So they would take like, there's some management system that knows like how much charge your battery has, and it'll try to keep it within some stable window where like you're not trying to decompose the material. So as long as we make better battery management systems, that should be fixed. Yeah, and sodium may have comparable effects in that like, because this profile is different for sodium versus lithium, it may be easier to check the state of health, but that's yet to be proven.
Another silly thing. Could it be possible to make a viable market using the weight of the batteries to do exercise equipment?
You should try it. Yeah, I haven't thought about that, but why not?
Might be one. One question from the Q&A is, why is lead energy dense, which is also a large atom, while sodium is not?
So I think I'm not as familiar with the lead acid chemistry, which I was referring to for like the lighting in your cars, which are powered by lead acid batteries instead. I think those batteries, instead of holding the ions like reversibly moving them in and out of these structures, they actually do chemical reactions. So because they do chemical reactions, you can store more lead per formula unit, and maybe it's more energy dense. But honestly, I don't know if lead acid is more energy dense. It's just probably cheaper for car lighting. Yeah, like the reason you don't have lithium ion AAA batteries, which are also, I think, lead acid, is because they're too expensive. And like, it's not like a cosmetic product. Like you can just use AAAs for lights, but batteries you want for slightly larger applications like your phone or your laptop.
And let's thank both of our speakers. Thank you so much, everyone, for stopping by for this month's Popping the Science Bubble seminar. While we wrap up, I'm just going to put up one quick slide that if you're interested in, you can sign up for our emails at this fancy schmancy QR code that we have right here. And perhaps a little bit bigger to make it easier. So our next seminar is going to be March 18th. I don't know if we have the speakers set for that just yet, but we'll get that sent out and you'll see it if you sign up for our mailing list once that is all ready to go. So thank you so much once again for coming out, and we hope to see you in a month's time.
Thank you.
Thank you. Good job. Sure, if you wanted that, I always like
Yeah, they have a panel on the bottom.
Um,